some of the more advanced stuff, as well as the Python coding courses there at the university. So I absolutely love teaching. In fact, when I retire, I'm just going to go back to teaching until I die at a university. So that's the general overall plan. But I also love meteorology. I wanted to be a meteorologist since I was 5 years old. I used to watch the Weather Channel on TV instead of cartoons when I was younger. So it's just been a deep passion of mine forever. I was also absolutely terrified of flying from my 20s into pretty much all of my 30s. So that's what prompted me to come here and learn how to fly to get over that fear, and luckily worked fantastic. So what do I do now? I'm a meteorological data engineer for a company that builds some weather software for other companies that trade on power, like solar, wind, load, that kind of stuff. So we build software to better predict what the weather is going to be like in a month, in 2 months, 3 months down the line, so that places like ERCOT would subscribe to it and get good weather data and good insight into what's going to happen. So that's what I do. So any questions before we get started? Great. All right, so I kind of treat this more of like an introduction to meteorology course over the next, we'll do this for 2 days, so this Saturday and next Saturday. I'll try and relate it to being a pilot as much as possible, but again, it's kind of more focused on if you were taking a class with me, and this is kind of what we're going over, because weather seems to be a really big pain point when you get to your oral exam. I've heard that the weather information can be pretty rough, especially if Sebastian could probably knock that out. It's a rough part of the oral exam. So I'm trying to give you a really good baseline knowledge so that you can, even if you don't know the information or know the answer to it during the exam, you have the building blocks to be able to piece that stuff together. So 6 hours here, 3 hours here today, and 3 hours next time, and we'll try and get through as much as we possibly can. So if this were a true course, we would start off with the layers of the atmosphere, because we got to know what we're talking about, the layers of the cake here. If we were in a geology course, we would also be doing the same thing. We'd be talking about the layers of the Earth as we go down. So I'm kind of old school. I love all I need to really do my job is just some markers and a whiteboard. And I don't like to write a whole lot of stuff on the board. A lot of what you want to take notes on are just kind of what I'm saying. If you need me to reiterate it, that's okay too. I don't like big giant walls of text, either on the board or whenever we get to some PowerPoint stuff, you'll notice it's just like us talking about graphs and stuff like that. So that's kind of my teaching style. So we'll start off here first with a graph showing the vertical layers of the atmosphere. So our vertical axis here is going to be Z. It's going to be our height going up, right? And then our horizontal axis here is going to be T for temperature. Now over here is going to be hot, and over here is going to be cold. I could put numbers up here, but honestly, you're not going to remember the numbers. So we're just talking about the relationship stuff, all right? So how many layers of the atmosphere are there? Anybody know? Good guess. Not right though. And also, no answer is bad, right? Making mistakes is how you learn. So please feel free to be as verbose as possible. Anybody? It's more than 3. 5, I will accept 5. I'll accept 5. I would honestly go with 4, but the fourth one can be broken up into 2, the very, very top one. So we'll go with that one here. So anyone know what our layer of the atmosphere is called, the one that we live in? It's called the troposphere. Also, my handwriting can get pretty rough, so if you ever need me to clarify, please let me know. So the troposphere, that's our home. That's our home. 99% of all the weather happens inside the troposphere. Some can go up into the next one, which we'll talk about here in a little bit. Now, what does temperature do in the troposphere? Y'all have all been in planes, right? You've had the doors off the remotes out there. You go up to 3,000 feet. What did the temperature do compared to what you were on the ground? What is it? Colder, right? So what does the temperature do in the atmosphere as we go up? Gets colder, at least here in the troposphere, right? So we'll have our line here, like that, right? So as we go up in the atmosphere, our temperature decreases. Our temperature decreases. Now, we can actually quantify that. We can go ahead and jump into something called a lapse rate. This is the change in temperature over the change in distance. I mean, typically when we're talking about a lapse rate, we're talking about a vertical distance here. So I'll go ahead and change in z there, z being our vertical axis. And our units for this are going to be degrees C per kilometer. So you can see kilometer being a unit of distance and degrees Celsius being our unit of temperature, right? So that's what our lapse rate here is. This line right here, this change in temperature as we go up, change in height, is what we define as our lapse rate. Now you've probably, how many of y'all been doing some cross-country planning? Right? What value do y'all use for looking at the vertical layers here, like what you're going to be at when you're doing like your pressure density altitude calculations and stuff like that? What is it? It's feet. What values here? Like how much per distance, what degree change are you looking at, do you assume?
2,000 or 2 degrees per thousand.
Yeah, 2 degrees. 2 degrees C per 1,000 feet, right? Y'all have probably used that before. What is that? That's a lapse rate, albeit a little bit different units because generally in meteorology we stick to using kilometers for everything, but 2 degrees Celsius per 1,000 feet. And I actually put some stuff over here, so 1 kilometer equals 3,300 feet, and 1 mile equals 1.6 kilometers. So we'll be revisiting this here in just a little bit, but that's essentially what we're talking about with this line. Cool. Now, we decrease and decrease and decrease and decrease, but then all of a sudden, up at around, I'll put some values here. This kind of varies based on where you are in the latitudes, but around 10 kilometers. 10 kilometers high, which 10 times 3,300 gives us 33,000, so right around 33,000 feet. And then you can then divide that 33,000 feet by 5,280, and you can get how many miles up that is, right? So right around this point, we transition into the other layer of the atmosphere, the next one. Anyone know what it's called? You've heard this word before. There you go, stratosphere. Stratosphere. Now again, 99% of all the weather happens down here in the troposphere. Sometimes you can get really, really strong convective storms, like really towering supercells, like these massive thunderstorms, and it can eject moisture up into the stratosphere, and you can actually get some little bits of weather that happen up here, but generally not very active as far as weather goes. What does the temperature do in the stratosphere? Like we're 10 kilometers up, so we're getting pretty close to space. What's the temperature of space? I'm not asking exactly, but it's super cold, right? It's like pretty close to like 0 degree Kelvin, like nothing, right? Super cold, as cold as it can get. So does it make sense when I say that the temperature in the stratosphere actually increases? It does. The temperature in the stratosphere actually goes up. So we generally assume a lapse rate in meteorology is a negative number, right? We're talking about decreasing temperature with distance or with height. So that's just the assumption. When I say the lapse rate outside right now is such and such, we're assuming that decreasing value, right? But whenever we're talking about a stratospheric lapse rate, we have to flick a switch in our brain. We have to say, oh my gosh, okay, so the stratosphere is actually increasing in temperature with height. So this ends up being a positive number instead. Now I don't actually know what the stratospheric lapse rate is, so we're not going to really worry about numbers with that. But anyone have an idea of why something's happening here? Why do we have a temperature increasing inside the stratosphere compared to the troposphere? We're closer to space. That doesn't make any sense. There's something there that protects you. How many of y'all are wearing sunscreen today? Nobody, right? Even at all the doctor's insistence. What is actually allowing you to kind of get away with not wearing sunscreen all the time? There's the ozone layer. The ozone layer is right there. It's actually right around right here. That's our ozone layer. Now you have a little ozone molecule right here, O3. And the sun's energy hits that ozone molecule. Now that sun's energy up here at the top of the atmosphere, very powerful. It's got a wide range of wavelengths associated with it. We're not going to get too much into it. But some of the higher intensity stuff like UV radiation, the stuff that we don't want impacting our skin all the time, that UV radiation is hitting that O3 molecule, that ozone molecule, and causing that ozone molecule to break apart. But it's absorbing that energy so that it doesn't impact us. That's why it was a big deal back in the 90s. How many of y'all are in your like mid to upper 30s? Am I like the only one? Okay. Anyways, back in the 90s, right, there was this whole ozone hole catastrophe that we were trying to avert. It turns out the refrigerants, CFCs, chlorofluorocarbons, the stuff that we would put in refrigerators or your car, back in the time it was made with chlorofluorocarbons, and that stuff was being released into the atmosphere and breaking down the ozone molecules up here. So bad news, right? So without that, this UV radiation actually gets down to the surface and impacts us and causes massive amounts of skin cancer and sunburns and all the other stuff. But as that energy is absorbed by our O3 molecule, our temperature, purple's not the best, our temperature is going up, right? Because it's absorbing that energy. So that's why our ozone layer here is causing the stratosphere to increase in temperature with height instead of decrease. Now the other thing I want to do here is I want to provide a name. So this right here, this dashed line, where our temperature is actually kind of leveling out, you can see our elapsed rate stalls. As we're going up in height, our temperature actually doesn't decrease or increase anymore. That's how we generally see where the tropopause is. So troposphere, stratosphere, this is our tropopause. It's where the troposphere stops and the stratosphere begins. And this is very important. Very important. So you can see up here we had another one of these. What do you think we call this line? Stratopause. Good job. Stratopause. And that leads us into the next layer of the atmosphere. Anyone know what it's called? I'd actually be kind of surprised if people knew what it's called. It's called the mesosphere. We won't spend as much time on this one. In fact, I would say we probably know the least about the mesosphere. There's not a whole lot going on up here. Balloons typically are in this range. Whenever we send up weather balloons, they pop generally like right around this area. And then you got your satellites and stuff up here and spaceships. And then you got all your ground sensors down here at the bottom. So really there's not a whole lot of sensing that we do in the mesosphere, but it's also just not really that exciting. Anyone know what the temperature does in the mesosphere? Have a guess? There's no ozone layer there, so decreases. It actually gets super cold. It actually gets super cold. Until we hit the mesopause. And then we get into the last layer of the atmosphere. What's it called? Anybody? It's called the thermosphere. Now we talked about earlier how it could be, you could break this one up into two different ones. So when people do that, they usually talk about the thermosphere, and then they break it up into like one right above it called the exosphere. There's reasons why you do it. It has to do with like radio occultation and some of the like stratifying of the material in this one, but generally when we're talking about temperature profiles, because you can see how are we dividing each one of these layers of the atmosphere? Well, yeah, the tropopause, but we're using temperature to do that. So the temperature doesn't change between the thermosphere and the exosphere, so which is why we generally consider it to just be one layer of the atmosphere. What's the temperature do in the thermosphere? We're right next to space. In fact, there's really no line that separates space from the thermosphere. So what do you think the temperature does?
It's basically zero.
Basically zero. That's a good guess. It actually does this. Thank you for participating. You know, every time I would give this lecture, I really count on someone following through with that. That's what you would expect to logically happen, right? We're right next to space. We're right next to space. Space is practically 0 Kelvin, not degrees Celsius. That would mean just like freezing. So I mean, we're super cold, right? We're very, very, very cold. What is that in degrees Celsius? Isn't it like negative 273 point something? Can't remember what 0 degree Kelvin actually translates to, but I think it's like negative 273 Celsius. So if we were in a plane, if we were in a special plane, or like a spaceship, or like the space shuttle, right? Space shuttle has wings. We're up here, and you opened up the window, and you stuck your hand out. What's going to happen to your hand? This is so much more fun when y'all participate. We're getting really, really hot up here, right? So what happens to your hand?
It would burn.
It burns out. Thank you for participating. Yeah, it's another curveball actually. Even though temperature up here is super hot, your hand will freeze. Your hand will freeze. And the reason because how do we define temperature? What does temperature actually mean, right? If you take this marker and you put it in the microwave and you increase its temperature, what are you actually doing to it? You're applying energy to it. You're causing the molecules that make up this object to start vibrating way more frequently, right? So temperature is a measure of the kinetic energy of a molecule, like the energy that's kind of keeping it vibrating and stuff like that. So up here in this area, how much atmosphere do you think is actually up there? Not a whole lot. Like this room is thick, right? We're all breathing perfectly fine. There's so much atmosphere in this room because we're at ground level. But when we're up here, you're now talking about like, there's a molecule, there's a molecule, there's a molecule. The density of the atmosphere is so low that even though each one of the individual molecules up here, if you measured its temperature, is really, really high, the amount of molecules there, you stick your hand out and you'll have like one impacting your skin like every couple seconds. Instead of how many are around my hand right now? Well, yeah, just huge number, right? Huge number. So, yeah, is it measurably hot up here? Heck yeah. But does that really matter in the long run? No, because there's so little molecules up here that it doesn't really matter. And we say all that because as we go up in the atmosphere here, what's happening to the density of the atmosphere? You have to account for this, right? The atmosphere is very bottom weighted. Most of the atmosphere is down here. And this relationship is actually exponential, which we'll talk about here in just a minute. Anyone have any questions on the layers of the atmosphere? All right, cool. There it is. So now that we have all that, we're going to come back down to ground level a little bit after we talk about how pressure works. And we'll come back to lapse rates here in just a little bit. Oh, right there. Okay. Pressure. Very important value, right? When you're doing your cross-country planning, you are looking at this quite a bit. Whenever you're keying into ATIS before you take off, one of the big things you look at is the pressure, right? You got to account for it. Pressure, if we define it mathematically, is force over area. Force over area. I can apply a pressure to this table, right? I can put some force on it. I'm applying a force over an area of this table, and I can apply some pressure. Common pressure units, inches mercury, kind of what we talk about all the time. Meteorologists, we don't use like 299 or anything like that a whole lot. We actually use hectopascals and millibars. So 1 hectopascal is equivalent to 1 millibar, and we'll typically talk in pressure in like 1,000 millibars, something like that, right? So if actually, let me do it this way. What's 299 or 2? Why is that number big? Why is it a big deal? Standard pressure, right? And that's what units? Inches mercury. Right? In meteorology, we would consider this identical to 1013.25 millibars. Right? So these numbers here are equivalent. Generally, when we're talking just colloquially, when we're just talking about pressure in general, we'll just consider that the atmospheric pressure at the surface is at sea level like 1,000. We'll just use that number. But this is a very, very important number that we'll hit on quite a bit as we go through. So this is our mean sea level pressure, like our average mean sea level pressure. Cool. So if I'm applying a pressure to an area, how am I getting atmospheric pressure? Like, we go outside right now, and in fact in here, there's a pressure being applied to us. We could look up what that pressure actually is. So that force being applied to us, if we break it up even more, you might remember this from physics class. Force is mass times acceleration. What's acceleration for the atmospheric air?
Gravity.
Gravity is our big one. So gravity is our acceleration, 9.8 meters per second squared, if I recall. And then what's our mass?
Us.
Well, no. Remember, this is the atmosphere, like we're measuring the atmospheric pressure. So let's say, all right, here's us standing on top of a big mountain, right? This mountain's like 14,000 foot high. So we're at the top of Pikes Peak in Colorado Springs. And then here's us down here in Austin or San Marcos, right? Which one's going to have a lower pressure? Up here. Why? Good. Why? Keep going.
Like there's less pressure, like as the density starts going up. As the altitude starts increasing, the density starts.
Okay, you're hitting on it. Look at this distance. That's 14,000 feet of atmosphere that if you were standing right here is above you towards space. So you have all of this compared to if you were standing here on this mountaintop, you only have to contend with this amount of pressure, this mass of the atmosphere above you. So smaller mass, much bigger mass. How does that translate to our force? If you're down here in San Marcos, you have a much bigger mass above you. So that means the force is much higher, which means the pressure, if you increase this number, is what? So if we have a higher number here, what does that do to this number? I don't know, too much math this morning? Yeah, increases. That goes up. So the amount of pressure that we're feeling is dependent on how much mass of the atmosphere is above us at any given time. So that leads us into a graph like this. So over here is going to be pressure for our x-axis. And then we think, oh yeah, we're going to do altitude over here, so z. So if we're at 0, if we're in Corpus Christi, down there at sea level, something like that, what's our pressure on average? Yeah, we'll just assume 1,000 millibars, right? So 2,909 or 2-ish. So we're right here, 1,000 millibars, so we have a dot. Now, as we go up in altitude, we expect pressure to do what? Decrease, right? I'll give you a helpful little thing here. For every 5.6 kilometers, we go up, the atmosphere goes down by half. For every 5.6 kilometers that we go up, the amount of atmosphere decreases by half. So if I go up to 5.6 kilometers, what's my pressure? Good. If I go to 11.2? 250. And again, what was that 16.8? 125. That's what our pressure looks like in our atmosphere. What's the significance here? Is this a linear line? What would a linear line look like? Straight, right? So do we have a linear relationship? What kind of relationship do we have? An exponential relationship. Why do we care about this? Why am I spending so much time on it? If I go from here, let's say I'm right here on this line, and we're maybe just like a kilometer up, something like this. And we go up 2 or 3 kilometers. How much pressure did we drop? Not to give me an exact number, that's a lot, right? That's like 300 millibars that we lost in pressure just by going up a little ways. Just by going up a little ways. What about from here? And we also go up the same amount. You see how that pressure change was much less? When you're in the lower portions of the atmosphere, that's where all the heavier stuff is. That's where all the heavier mass is. Gravity's pulling all that oxygen, the nitrogen, everything towards the surface, right? So when you go up in pressure or up in altitude here at the surface, you're actually decreasing in pressure much more rapidly than if you were up here at the top of the atmosphere. And that has big ramifications, right? Big ramifications. Any questions on that? All right. Let's talk about tropopause height. We're just setting some basics right now. Let's do another graph here. All right, I'm going to draw. So hold on before you draw stuff. That's our Earth. And this is going to be the North Pole. This is going to be the South Pole. So we've got our Earth, but we've kind of tilted it down. And this is our equator. Right there. We've kind of tilted it on its side. Now, what was the tropopause?
The one ring.
The what?
The part of the atmosphere.
Yeah, that's a part of, so that's the troposphere. And the tropopause was the top of that layer, right? And we said that 99% of all the weather happens inside the troposphere. So that tropopause is like a barrier that prevents the weather from going up into the stratosphere most of the time. Most of the time. So it's important for us to know, does that tropopause actually change with height or change with latitude, right? So that tropopause, if we kind of graphed it out, at the North Pole, the tropopause right around here is 6 to 8 kilometers high. So right there. In the mid-latitudes, the tropopause is between 10 and 14 kilometers high. And then at the equator, it's like 14 to 16 kilometers high. So we end up with this. So the troposphere, and coincidentally the entire atmosphere, all the layers, are bulging out. They're actually much thicker at the equator and the mid-latitudes than they are at the poles. Why would that be? You have a guess? What's the most immediate answer? And it's going to be correct. Temperature, right? Temperature. How does a hot air balloon work?
Hot air.
Why does the hot air make what yeah?
Hot air is produces less pressure than actually.
Yeah, it's less dense, right?
So it goes up.
Yeah, yeah. If I have a bubble of hot air right here that I heat up, convection will be created because this bubble of hot air will actually start rising, right? It's less dense than the environment. We'll get really into this later. But here, the sun is constantly hitting more directly our mid-latitudes and our equator here. So we're actually heating up that air considerably. And that's causing it to expand, to be less dense. So our atmosphere actually bulges out. Now, if you took all of this and you sandwiched it down, you end up with the same amount at both of these, all three of these locations. But just because it's hotter around here, we're actually causing that tropopause to increase in height. Now, why does this matter? Let's say we have some storms come through today. And we look out on the horizon and we see like a little storm like this. Is that severe? Does it look severe to you? Not really, right? But what if we had a storm that looked like, I'm going to scale this down just a little bit. So here's our little storm that we were just talking about. What if we had something like looks like this? Y'all seen stuff like that, right? Over the course of your life, you've seen some big towering thunderstorms. Which one's more severe? The one on the right. In fact, this storm here, have y'all seen this anvil on the top of storms before? It like hits some kind of a barrier and then starts spreading out laterally. What do you think that barrier is? It's hitting the tropopause. It can't go above it, so it hits it and then spreads out, right? So if we had to just assign a severity level here, would we assume that the amount or like the vertical height of a storm matters for its severity? Would a taller storm be more severe than something that's shallower? Definitely, definitely. So if this is the maximum height right here that a storm could get at the poles, and this is the maximum height a storm could get at the equator, which one's going to have more severe weather? The equator, definitely. Now it ends up that we actually get the most severe stuff here in the mid-latitudes, even though our storms can't actually get as high as they would in the equator. But that's because here we have a really good balance of cold and hot air, which that battle between cold and hot air and density and all that really helps make storms pack a good punch. So that's just how it ends up being. But this is why the tropopause is super important. Any questions? All right. So let's talk about temperature inversions, and then I think we're good to jump into moisture. All right, we talked about lapse rates. What's the definition of a lapse rate? What are the units?
Changing temperature over changing height.
Yeah. Degrees Celsius. And we usually use degrees Celsius per kilometer, but as we see, we can use degrees Celsius over feet over there as well. So that's what our lapse rate is. Now, if we go back to this graph, temperature, Z, and we're just looking in the troposphere. We're not worrying about all the other layers of the atmosphere. We're just looking inside the troposphere here. And we have our, I'm going to draw a couple lines here, just so you know. Our typical one will look something like this. And this is where our tropopause is, right here at that location. That's what our typical lapse rate looks like. We can define this. We say the average tropospheric lapse rate equals 6.5 degrees Celsius per kilometer. That's the average tropospheric lapse rate. That's a good one to throw into your brain. We're going to be talking about that one a lot over the next 2 class days. Average tropospheric lapse rate. So for every 1 kilometer that we go up, we're going to decrease by 6.5 degrees Celsius. Does that make sense? What number have y'all been using? If 1 kilometer is equivalent to 3,300 feet, so that'd be 3,300. So that'd be 6.5 degrees Celsius per 3,300 feet. What does that actually work out to? 2 degrees per 1,000 feet, roughly. Right? So verified, that works out. Now what if we had something like this? I have my temperature here. Again, I'm drawing another line for like a totally different day. What if I had something like that? Not uncommon at all in the atmosphere. This is called an inversion layer. Inversion layer. So here, our temperature is decreasing as we go up. What's our temperature doing right here? Increasing as we go up. Increasing as we go up. Have y'all learned a little bit about stability? Does that kind of ring a bell? Maybe you've been studying it a little bit. It doesn't make a whole lot of sense. It's one of the harder things to understand in meteorology. This creates a stable environment. Because all of a sudden, things that are rising, like air parcels that are rising, can't rise above this. This is like a capping inversion on the atmosphere. This is very common in the mornings. If you ever wake up in the morning, like even this morning, you woke up and you looked up and it was just all overcast, right? But above it was nice and clear. It'd be nice and clear all the way up to the top of the atmosphere. That's because we get this low-level inversion that sets up in the evening time. So, very common. Any questions? Now there's 2 more lapse rates that we're going to talk about. But we're going to save that for whenever we talk about clouds. I don't want to throw tons of numbers at you right now. But this is the average tropospheric lapse rate. The other ones we're going to talk about are going to be the moist adiabatic lapse rate and dry adiabatic lapse rate. But again, those will come here in just a little bit. Let me make sure that we've covered everything in the beginning, and it looks like we have. All right, you want to take a 5? Take a 5, go get some water. Be back right at the, just a little bit after 9. Got that.
Do you have any other ratings besides private pilot?
No, I just have sport pilot. See, I'm not even a private.
Sorry.
That's because the FAA is in the dark ages with mental health. So an anxiety diagnosis 20 years ago is just going to make it really hard for me to get a private pilot's license. So, which is fine. I only started doing this because I wanted to get over the fear of flying, and I ended up finding a really cool hobby. So yeah, it's a blast. But that's okay. I don't need to fly with more than one other person. I don't need to fly into clouds. That seems like death. So it's okay. I'll leave that to professionals. But who knows, if they ever really reevaluate their stances on like anxiety and stuff like that, I'd go for it. Are you going all the way? All right. You going military or are you going?
That's where the road kind of splits from me.
Yeah.
Look at all my ratings.
Cool. How old are you?
16.
Man, you got so much ahead of you.
Yeah, it was either my driver's license or pilot's license. So it was a really easy decision for me.
Really? You had a choice?
Yeah.
Interesting.
They just really didn't want to put me on the insurance yet.
Yeah, okay. Gotcha. Yeah, that's rough. That's rough. I think we're still missing just one person, so as soon as he gets back, we'll start.
Yeah, I got that.
Is it going to calm down next time? Is it going to calm back down?
You mean today or just generally? Oh, I don't know. I didn't actually look at the weather this morning. I looked at it today. It was supposed to be windy all day. Like as we get into the afternoon, the heating up is going to cause the wind to go up. What is it right now? Gusting 19? I mean, I would expect it to go up to like 25. Yeah. I haven't really had a good high wind day since prepping for the check ride, so it'd be good just to get out there and. It's been, yeah, I've just having like low wind days constantly for the past 2 months. That's all right. We're going to get back to our heat dome here in July, and things are going to be clear and not very windy for the summer. Okay, next. This is actually my favorite topic to cover in meteorology, even more so than severe weather and lightning and tornadoes and all the other stuff. This might seem super basic to you guys too. Like, why do I care about mixing ratio and saturation mixing ratio and dew point temperature and all that? That sounds super, super boring. But to cover everything in meteorology, we have to understand this heat transfer process. And to do that, we have to understand when we're changing our phases, because water means everything in meteorology, right? Everything comes down to, are we dealing with water vapor? Is there water vapor in this room? Can we see it? No. Why?
It's not right there.
Well, you can't. Yeah, you can't see it, right? You can't see it. It's water, little water droplets, like water vapor molecules. Not actually droplets. That's incorrect. Don't write that down. But water vapor molecules are flying around this room right now. There's a humidity, right? We can measure that inside this room, right? What would this room look like if we had liquid water floating around?
There'd be dew everywhere.
We'd have some dew, probably. Have y'all been in an environment where there's liquid water in the air? Anyone tell me when that environment is?
Rainforests.
Yeah, sure, maybe. Have y'all been in fog before? Been walking around in fog? That's liquid water droplets surrounding you. You're in a cloud at that point. There's no difference between fog and a cloud, right? That's what that environment is. When you're in the morning and you turn on your water faucet and your whole bath, you close your bathroom door and the water just like you walk in and we call it steam, right? But there's just like liquid water everywhere. You're in a cloud. That's liquid water. What's solid water?
Ice.
Ice, right? We deal with ice all the time. So everyone kind of understands what those three phases are. We have water vapor, which we can't see. We have liquid, which we can see as cloud or mist. And then our solid, which is going to be our ice. So can we go between all these? Can we transfer between them? What's it called when we go from a gas to a liquid? With confidence. That's incorrect, but I'm glad you had confidence, right? What is it? Condensation. Condensation, right? Keep saturation though. That will be an answer to a question I asked here in like 10 minutes. What about liquid to solid? Freezing. What about solid to liquid? Melting. And what about liquid to gas? Evaporation. Great. We don't really need to cover examples of these. We kind of see them all the time. And y'all are 15 plus, so you've probably seen this eventually. But are these the only ways that we can go through this process? We can skip liquid. We can skip liquid. What's this one called? Gas to solid. I'd actually be very impressed if someone knew this. And the other one too, honestly. Is there things that you really...
Sublimation?
Oh, that's a good guess. Sublimation is going to be this one. But we can go ahead and do that one. Sublimation. Solid to gas. It's weird, right? That's really weird. Two examples come to mind. Let's say you have an ice cube and you stick it in your freezer. And you come back and check your freezer in 3 months. Is that ice cube still there? Just that sole one ice cube? Might be, might not be. It's definitely going to be smaller though, because it was undergoing for 3 months sublimation. It was giving some of itself off. It was doing this gas to solid, solid to gas transfer. The other big one, how many of y'all dealt with dry ice before? What is dry ice? Dry ice? Yeah. What is it? Is it ice? Is it water? No, it's CO2. It's solid CO2. So if I had a piece of dry ice right here, it would just eventually disappear because it's just sublimating itself. It doesn't go to a liquid phase before it then goes to a gas phase. Because of and you probably learned a little bit in physics and chemistry and in school, there's like this whole triple point graph where it actually just skips going into that particular phase. So that's an example of sublimation. What about this one? The top one. Deposition. Deposition. And we can remember that because it's depositing as a solid. So it's gas directly to solid. And a good example of this, if we have like a really moist environment, but it's a really cold morning, below freezing. So say we just wake up and we go outside and the grass is covered in, well, it's below freezing, so frost. Frost is a really good example of this deposition here. You might not have had any rain or anything like that happen overnight, but all the grass on the ground is still or it's frozen, right? So you had this process occurring, deposition, where the water vapor molecules were actually making contact with the grass. The grass was cold, so it deposited onto the grass. It didn't freeze. So we can really take our glasses and put them on and like push them up against the bridge of our nose. And we can get really, really technical with the verbiage there and just say, well, it deposited and didn't actually freeze, right? So that's our process. This is what we really care about, though, is how heat is transferred whenever we do these processes. So when we go from gas to liquid to solid, we're going from a gas, which has a lot of freedom, right? Has a ton of freedom. There isn't a whole lot of molecules like this being held together in a very rigid structure like a solid, right? This can't, unless we heat it up and turn it into a liquid, it stays this shape. It has very, very strong bonds keeping it together. What about a liquid? There's still some bonds keeping it together, but it can kind of do a lot more than what a solid can, right? And then a gas is totally free. It can do whatever it wants. So how we transfer between these different phases is really important. So if we were to go, which way do I want to go here first? Yeah, let's go this one. Let's go from solid to liquid. So let's say that we melt it, or we go from liquid to gas. We undergo some evaporation. So what I'm doing is I'm taking this solid and I'm turning it into a liquid. What I have to do is I have to apply energy to it. So let's say these are two bonds, right? One molecule, molecule, and there's a bond right here. I have to apply energy to break that bond. So I have to apply heat energy. We can heat it up. That's one of the ways that we can apply the energy to it. So if I apply that energy and I turn it from a solid into a liquid, what happens to heat in that process? Can we have a guess? Does it get consumed or does it get released? Again, I'm doing this. I'm going consumed. I have to apply this heat energy to it to break that bond. So heat actually gets consumed. Right now you're thinking, why do I care about that? That's okay. What do you think happens in the other one? The other way? Going from gas to liquid or liquid to solid? Heat's released. As an example, not going to actually do it. Let's say I take this little cup of water here and I pour it on the ground. I now have a puddle of water on the ground. Or I go outside and do it. Probably Sebastian would like that better, right? So I pour it outside. The sun's hitting it, right? What starts happening to it? Even if I poured it in here, the same thing would happen to it, but it happens faster outside. Evaporation, right? We start going from this liquid to gas phase. Now, if the temperature, if I measure it right here, is I'm actually kind of warm up here, like 85 degrees, right? And if I then, after the evaporation has been going on, and I take a thermometer and I measure the air right above that puddle, what do you think the temperature is? Do you think it's also 85? Do you think it's higher than 85? Do you think it's lower than 85? It's lower, right? Because when we're going from liquid to gas, we're consuming heat. So the actual act of evaporation is causing temperature to decrease. Now let's say right outside we have a rainstorm come through. Lasts 10 minutes, really quick. And then it goes away and then it becomes sunny outside. You walk outside, what do you think you feel? Do you think it feels cooler? Or do you think it feels hotter? It probably feels hotter, but that's because now we're evaporating all of this extra moisture into the air, so your body can't sweat as easily and get rid of its own heat. But if you measured it outside, if you actually took the thermometer outside, you would see that it's actually cooler than prior to the storm coming through. So that's what this really, really matters here. The other one here is whenever we have cloud formation, we're actually doing this condensation process. So the actual act of creating a cloud adds heat to the environment. So again, these are just building blocks that we're going to be talking about a lot later. But whenever we make a cloud, we're adding heat to the environment. Any questions on this? All right. Probably a lot, but that's okay. All right, let's talk about mixing ratio. Now, if you look this up, lots of other places, you're not going to see this actual qualifier here. That's what I'm adding to it to separate it from what we're going to talk about next, which is saturation mixing ratio. Mixing ratio, how many of y'all remember this term from high school or college? You glossed over it. They're like talking about the mixing ratio of a substance. You didn't care. You just wanted to get out of class, right? It's a term. It's the amount of something in something else. You can write that down as like a definition, right? Amount of something in something else. We're like relating two quantities. The typical units for this are going to be grams per kilogram. That's what we're going to care about in meteorology. Grams of something in kilograms of something else. You could also see this as kilograms of something in kilograms of something else, or micrograms in kilograms, or whatever. You can have this whatever ratio that you end up wanting to do, right? In meteorology, we care about water vapor, the amount of water vapor in dry air. So we'll do dA for dry air. So the amount of water, the grams of water vapor in kilograms of dry air. How's it feeling here, moisture-wise? Does it feel a little humid? Maybe just a little bit. If we were to describe the mixing ratio in this room, would you say it's like average? Would you say it's above average or below average? Like high, low, just about right? Again, we're talking about the amount of water vapor in the dry air in this room. No gotchas here. Probably a little higher, right? So right now I'd say in this room we have a little bit higher than normal mixing ratio. Now what if we went down to Corpus or Houston and we went out and we actually sampled the water vapor, or sorry, sampled the mixing ratio? Do you think it'd be higher than here?
Yes.
Yes, right? Houston's awful. I don't know anyone lives there. I lived in Corpus for 6 years. It was pretty rough there too, but yeah, Houston's mixing ratio is just constantly really high. That's also just a testament to living in a maritime environment. If you went to Seattle, or if you went to San Francisco, or you went to Corpus, or you went over to New York City, if you're next to a large body of water, you constantly have this evaporation process adding moisture to the air. So you're just going to generally have a higher mixing ratio than what you're used to. Now, let's say I go up to Denver. Much more continental environment, right? There's not like large water bodies anywhere near it. So do you think the mixing ratio up there is high or low?
Low.
Low. So we already have a feel for what mixing ratio actually means. The difference here is we're not talking about relative humidity or anything like that. That's a really complicated term, actually. We're going to talk about that here in just a little bit. But we're talking about mixing ratio. This is something that I can have a specialized probe or a sensor tell me what the mixing ratio is inside this room. It's a quantity. It's an actual value, right? So that's what our mixing ratio is here. And we already got a feel of like what that means, like increasing it, decreasing it, etc. Any questions? Cool. I feel like I'm forgetting something to talk about on this, but I'm thinking ahead. I can't think of anything else that would need to be said, but we'll cover it if it pops up. The next one here is going to be saturation mixing ratio. Now, whereas actual mixing ratio was me sampling what's in this room right now, a quantity, saturation mixing ratio is not like that. Saturation mixing ratio is a limit. It's a limit. It's a line that we cross. So, I'll give you the units here. It's also grams water vapor per kilograms of dry air. So same thing. And to understand this, let's talk about tea. How many of y'all like tea? Maybe y'all drink sweet tea. Oh, you got some tea right there, right? How many of y'all have drank sweet tea before, even if you don't really like it, right? When I passed 30, I had to give it up. I mean, it's just, you have to make sacrifices once you start getting older, right? I used to just drink unsweet tea now. McAllister's tea, incredible. Stop there all the time. So, let's say we're making tea. Well, actually, let's say that we go to Denny's, and you ask the waitress for some sweet tea, and she's like, great. Even though this is Texas, and they should have sweet tea back there, she brings you a cold glass of iced tea, unsweet, and some sugar packets. Can you make really good sweet tea with that? It's pretty tough. How many of y'all tried? Yeah? So you open the sugar packet, and you pour it into the tea, and you stir it amongst the ice cubes, and what happens to all the sugar? Yeah, it just sinks. Doesn't really dissolve into the tea. You take a swig of the tea and you're like, oh, this is still pretty much unsweet iced tea, right? So obviously temperature has a problem there. Temperature has a problem. In this example here, how many of y'all remember what the terms here are in our mixing ratio? This was called the solute. And the solvent. Right? So the solute is the thing that we're adding, and the solvent is the thing we're adding to. So in our example, we're not talking about meteorology, we're talking about tea. The thing that we're adding is the sugar, and the thing that we're adding it to is our tea, right? Analogous to our water vapor and dry air situation. That's what we're kind of relating it to. So we start off with a ton of tea, and we add some sugar into it. It's really, really cold tea. We add the sugar to it, and it just kind of dissolves out. It just precipitates out. It doesn't actually dissolve. So that's bad. So we can obviously say that it being colder makes it harder to get that top value into the something, right? What about if we heat it up? How many of y'all have made sweet tea before? What do you have to do to it? Yeah, you boil the water and the tea, and then you can grab a whole cup of sugar, you pour it into it, you stir it, it all goes away, it dissolves, right? You take another cup of sugar, you pour it in, it dissolves. Eventually, you're going to pour a cup of sugar into it, and what's going to happen? You're not going to dissolve it. It's because some of the sugar is going to settle to the bottom. But if we increase the temperature, we increase the amount of stuff that we can put in the tea. Increased amount of stuff. In each of these limits here, whether we're doing a cold glass of tea or a hot glass of tea, we hit a value, we hit a word at the end of it. So with that cold glass of tea, you poured the sugar into it and you stirred it and it all just went to the bottom. You already hit saturation. Saturation is us hitting that limit of the amount of stuff that we can put in that substance. Once we hit saturation, we can't put any more into it. But we can increase that saturation limit if we increase the temperature. Everyone cool on that? All right. So increasing temperature increases our saturation limit. And then decreasing temperature decreases limit. Now let's bring this back real quick to water vapor. If I heat up this room, which it's already kind of hot enough, right? If I heat up this room, I can put more water vapor in here before I hit saturation. What would saturation look like in this room if we hit it? That magical number. I heard it. Fog. We would start seeing fog everywhere. There'd be liquid water droplets analogous to the sugar just precipitating to the end, to the bottom of the tea. If we hit saturation in this room, it would now be water droplet city. There'd just be tons of it everywhere. Just streaming around. It'd be water, like just fog, essentially. It'd be a cloud, right? Up until that point, though, it was like this, completely, we call it dry. It wasn't saturation. Does that make sense? So for us, once we get that liquid water droplet stuff precipitating out into the air, which not to be confused with precipitation, that's a different process. But once we get those little liquid water droplets in the air, that means we've hit saturation. All right. All right, let's relate these two. Y'all have heard this term all the time. Relative humidity. It's one of the most misunderstood terms in meteorology. Meteorologists even use this term wrong all the time. Relative humidity measures how close we are to saturation. That's all it does. Measures how close we are to saturation. So if we have relative humidity, we can define it mathematically as the actual mixing ratio divided by the saturation mixing ratio times 100%. We've talked about both of these. Remember, actual mixing ratio is the actual amount of water vapor in the air. We can measure it. Saturation mixing ratio is the maximum amount of water vapor that the air with current properties can hold before we hit saturation. So, let's say the air can hold half as much. Let's say the saturation mixing ratio in this room right now is like 10 grams per kilogram. And we measure the actual mixing ratio to be 5 grams per kilogram. What's our relative humidity? Five divided by 10, 0.5, right? Half. And then times 100% gives us 50%. 0.5 times 100% gives us half as much. So we end up getting 50%, right? What if we packed it in here? What if we opened up the windows and we had just a really strong Gulf breeze coming up from the Gulf and it was just like flooding this place with moisture? So we ended up with, instead of 5, we ended up with like 9 grams per kilogram of water vapor to dry air. So 9 divided by 10 gives us 9/10, which is going to be 0.9. And then times 100% gives us 90%. So you see how this number comes to be, right? If we walk outside and it's 90% humidity, relative humidity outside, how do you feel? Feels like shit, right? It's awful. Your body can't sweat, it can't get rid of the heat, so you feel you feel like cloyed, right? You can't, it just feels gross. It feels like Houston, right? But let's say we go up to Abilene or Lubbock. They're typically on the other side of the dry line, which we'll talk about next time. So their relative humidity is typically like 10 to 20%. How does that feel? Feels really good. Feels very dry, right? If you work out and you start getting beads of sweat all over your body, the beads of sweat actually go away. They evaporate very quickly, causing that transfer of heat, which is why you sweat. It's removing heat from your body. Remember, evaporation consumes heat in that process, right? So you end up feeling really, really good. So that's what our 10% or 20% relative humidity means. So that's what relative humidity is here. The problem with relative humidity, though, is we have units of grams per kilogram over grams per kilogram. So when we do this division, what happens? What happens to these units? They go away. And all we're left with, is the percent. Why this term is misused all the time is because this tells us nothing about how much water vapor is actually in the air. We can't make that assumption because it all went away, right? If I have a relative humidity of 90% up in Seattle during the fall, but then I have a 90% humidity down here in Houston also during the fall, which is still pretty hot down here, right? Is the amount of moisture in both of those environments the same? Which one's going to have way higher moisture in the air? Houston's going to have way higher moisture in the air, right? So that's a big deal. That's a big deal. What do you think your plane cares about? Your plane cares about this number, the amount of moisture in the air. So if you're accounting for the density of the air differences because you have a lot of moisture in the air, you don't want to use relative humidity. You want to use like actual mixing ratio. You want to have that actual value. Any questions on this? All right, how do we change this? How do we change relative humidity? This is a big one. This is going to lead into for the rest of the talks today. We're actually doing really good on time. There's two ways. Got it. Temperature's a good one. Temperature's a good one. So we'll make a new section here, changing relative humidity. In mathematics, a triangle typically means change. I think I forgot to tell you all that whenever I drew a triangle earlier, but you'll probably got it from the context clues. So changing relative humidity. We can use temperature. We can increase temperature. We can decrease temperature. Right? So what happens when we increase temperature? We know that relative humidity over here is built on two different things, actual mixing ratio and saturation mixing ratio. Does us increasing the temperature do anything, giving you some context here, some inflection, right? Does it do anything to actual mixing ratio, to the amount of moisture that's actually in the air? No, it does not. What does it affect though? Saturation. What happened to our tea when we heated it up? Yeah, we could increase the saturation limit. So increasing temperature here increased our saturation mixing ratio limit. So increasing temperature increases saturation mixing ratio. Does that make sense? That's very important. Does anyone not really want me to go over that a little bit better? Adding temperature to our tea, boiling it, allowed us to put more stuff, more sugar into the tea before we hit that saturation limit where all the sugar started just like falling to the surface, right? Same thing with air. Increasing the temperature allows us to force more and more water vapor into the air. So if we increase saturation mixing ratio, this number goes up. What does that do to this number? We're dividing by a bigger number. So instead of like 1 over 2, we're doing 1 over 4. It's going to go down. So if we increase temperature, we increase saturation mixing ratio, and our relative humidity is going to go down. This morning, when we woke up, if we measured the relative humidity outside, what do you think the relative humidity was? Right after the sun started coming out, just right at dawn. 70, 80%, pretty high, right? It's not uncommon for us to actually hit 100% humidity just before dawn. It's very typical, especially in a moist environment like Corpus or Houston, right? Sun came out, temperature started going up, saturation mixing ratio started going up, and our relative humidity dropped. If we looked at an actual graph, we'd see that we probably started the day at like 70, 80%, and now the relative humidity outside is probably in like the range of like 50, something like that, like 50, 60%. So that's pretty typical. What about the other one? Temperature going down. What does that do to saturation mixing ratio? Goes down. If saturation mixing ratio goes down, if we're dividing by a smaller number, what does that do to this number? Goes up. Goes up. Trying to think of some good examples. This one's really good. How many of y'all been in a cold environment before? Like you went up to the mountains, you were in an environment where you could actually see your breath. Have everyone done that? Okay. So you're breathing out air, right? What's your body temperature? 98.6, right? So the air that you're breathing out is probably right around that number. So you made this little bubble of air like this, came out of your mouth. It's 98.6 degrees, we'll just assume, right? You're in a cold environment. You're up in the Rockies, it's like 28 degrees Fahrenheit outside. So as soon as this little bubble of air comes out of your mouth, what immediately starts happening to that bubble of air? Well, now we're getting there. Temperature starts dropping, right? So a little bubble comes out, temperature starts dropping. Saturation mixing ratio, the amount of stuff it can hold, we're now dealing with the iced tea rather than the hot tea, right? Can't hold as much stuff. So then that causes saturation mixing ratio to go down, which then causes relative humidity to do what? I know it's on the board, I'm just trying to get some like reinforcement here. What does it do? Goes up. It hits 50%, 60%, 70%, 80%, 90%, and then it hits what? 100%. When it hits 100%, we've now, I don't have it on the board here anymore. We've now hit saturation, 100% humidity. What happens to that little bubble of air that was invisible? This all happens really fast, so it's not like you're actually seeing like a little bubble of air just appear in front of you, but that little bubble of air is now a condensed little cloud, right? Because you hit saturation and you had condensation occur. Now eventually it disperses and it goes away. There's too much dry air, the dry air amount increases here, and this number goes down. But yeah, everyone cool with that? It's a good example. All right, what's the other way we can change relative humidity? We're spending a lot of time on this because it's really important. There we go. Moisture is the big one. This top term. We can add or remove moisture. Let's talk about the top one. We add moisture. In the morning, you wake up, you've had the air conditioner on all night, it's nice and cool, right? You go in and you start the water, you turn the water on, you put it on maximum setting. It takes a long time for your plumbing to heat up, so you just kind of get it going, right? You leave your bathroom, you close the door, you go get your coffee pot started. And then you come back after like 3 or 4 minutes. I know, environmentalists get mad at you running the water for that long without actually getting in and using it. But you walk back into your bathroom, what's happened to your bathroom? Yeah?
Temperature's higher.
Well, temperature's probably a little higher, but what's in your bathroom now? We call it steam, colloquially, yeah. But just cloud, You've made a fog in your bathroom. How did that occur? Your water faucet at the top of your shower is constantly shooting out water, filling up your bathtub and going into the drain, et cetera, et cetera. But a lot of that's aerosolizing and increasing the amount of moisture inside of your bathroom. So this number is going up. If this number is going up, which term over here does this affect? The top one. What's that going to do to that term? Remember, this is the measured amount of moisture in the air, the grams of water vapor per kilogram of dry air. So if we're increasing moisture, we're adding water vapor to the environment, what's this number going to do? Go up. Good. So actual mixing ratio goes up. And if actual mixing ratio goes up, what happens to this number?
It goes up.
Goes up too. And it hits 50%, 70%, 90%, 100%, and then what's our bathroom filled with?
Fogs.
Yeah, fog. We've hit saturation at that point. And the other way is true. If we remove moisture from the air, or remember that actual mixing ratio is grams of water vapor per kilogram of dry air, grams water vapor per kilogram of dry air, we don't have to add moisture or remove moisture. We could also do something to this term. We could add dry air to it. That's equivalent to like removing moisture from the air as well. So one of those ways, if we decrease moisture, we decrease actual mixing ratio, and then we decrease relative humidity. So moisture and temperature. Any questions on that? Does that all make sense? Are y'all glazed over yet? We're an hour and a half in. We'll cover just a little bit more and then we'll take a break. We'll do some jumping jacks. Okay. Last term. What's reported on ATIS? Do they give you relative humidity? Do they give you actual mixing ratio? Saturation mixing ratio? They give you temperature? Okay. What else do they give you? Dew point. They give you the dew point temperature. What units? What do they tell you? They're like temperature 28 degrees Celsius, and then dew point temperature. Do they give you like 48 or like or do they give you like 25 grams per kilogram? What do they tell you? It's a temperature. It's a temperature value. So it's a degree temperature. That looks like I just drew it randomly, but it's the units. Oh, actually, I should do this. The units are degrees. It's a temperature. So what is a dew point temperature? Typically, I don't like to write out a lot of stuff. So whenever I do, it's kind of important. But just to get us the definition here. It's the temperature we need to lower to in order to hit saturation. The temperature we decrease to in order to hit saturation. Your dew point temperature will always be equal or less than your temperature. Your dew point temperature will always be equal or less than your temperature, not higher than your temperature. So let's say they tell us that our temperature outside is 25 degrees Celsius. Does that number mean anything to anybody in this room? How many of y'all are coming from outside the US? You spent a lot of time outside the US. Anybody? Nobody? Oh, you did? Are you familiar with, like, if I told you 25 degrees Celsius, you'd like have a feeling for what that feels like outside?
It's
Yeah.
pretty much a little bit like
Yeah, yeah.
Relatively colder.
Yeah. We, growing up here, we don't deal with Celsius all the time. Yet you're being forced to use Celsius for all of your flight stuff as well. So it's kind of confusing, right? The way that I know to feel this out is double this number in Celsius and add 32. And that gives you roughly, it's actually a 5/9 ratio, but it's pretty roughly accurate. So double this, 50, add 32, gives us 82, right? So roughly 82 degrees Fahrenheit. So it's 25 degrees Celsius outside, and that's our temperature. And then ATIS also tells us that the dew point temperature outside is 20 degrees Celsius. Now for dew point temperature, we typically do a T with a little d, subscript d, and that gives us our dew point temperature. So what's this telling us? Our dew point temperature is the temperature we need to lower to in order to hit saturation. Are we at saturation right now? No, right? We need to lower this number to this number, and then we'll have saturation, right? So bring out the temperature one. If we decrease temperature, and our relativity equation's over here. Actually, I'll go ahead and add it over here since we're saving it. If we're lowering our temperature, which value does that affect? Top or bottom? Actual or saturation? Saturation. What does it do to it? We're lowering the temperature. We're dealing with iced tea instead of hot tea. It holds less, so our saturation mixing ratio is lower. Goes down. And if saturation mixing ratio goes down, what does that do to this number? Goes up. So we're lowering our temperature to 24 degrees, 23 degrees, 22, 21. And in that process, our relative humidity is going up and up and up. We're getting really close to 100%. And when our temperature is equivalent to our dew point temperature, or we hit 100% relative humidity, we hit saturation. Does that make sense to everybody? So that's what our dew point temperature means. Now let's say our temperature outside is 25 degrees Celsius, and we just had this cold front come through the previous day, so we have a lot of dry air in the air, and our dew point temperature is actually like 5 degrees Celsius. So 25 and 5 degrees. Do we have to cool down a ton in order to hit saturation? Oh yeah. We'd have to bring in a lot of cold air from somewhere. Or we could actually bring in a lot of moisture from somewhere and cause our dew point temperature to go up. So we use dew point temperature as like a pseudo moisture level, right? If I say that the dew point temperature, we'll switch to Fahrenheit here. If I say the temperature outside is 90 degrees and the dew point temperature outside is 78 degrees, 78 degree dew point is really high. It's really high. Getting up into the 80s is exceptionally high, right? But if I say the dew point temperature outside is like 35 degrees, that's what it would typically be like in Lubbock or Abilene, something like that, if they're on the other side of the dry line. That's a really low dew point temperature. So everyone got a good feel for that? All right, let's talk about cloud formation, and then we'll take a break. This is the fun part. Well, I think the previous stuff was also really fun, but I don't know, it's very academic, and maybe y'all didn't really want to do that this morning. Okay. Bring out all the colors. Here's our ground. Let's talk about air parcel theory. We kind of already been talking about it a little bit. In meteorology, we have to make everything very textbook. So that means I have this air parcel in front of me. It's this big bubble. I've cut it off from everything else It's just this invisible glass, plastic, whatever force field bubble that I have in front of me, right? The dew point temperature inside of it is what it is. The temperature inside of it, the amount of moisture, everything is in it, right? I can take this bubble on a trip. I can take it over to Corpus. I can take it over to Lubbock. I'm keeping everything inside the bubble, what's in the bubble. Everyone cool with me? That's called air parcel theory. So, on the ground, I have this bubble on the ground. It has some characteristics, some parameters, some variables, you know, temperature, dew point, whatever, whatever. Along comes something. Something happens. We call these triggering mechanisms, which we'll talk about probably at the end of today, maybe tomorrow. Along comes something and causes this bubble to go up, to rise into the atmosphere. Now, as this bubble starts to rise, we know in the atmosphere what happens to temperature. We're in our layer of the atmosphere, right? Tropopause, tropopause is up here. So this is our troposphere. So what happens to temperature as we're going up? It decreases. Now, before you write that down and draw it, I'm going to leave a space right there, right? I'm going to intentionally leave like a slot for something new that we're going to add. But temperature here decreases. We're essentially going to explain why temperature decreases here in just a little bit. So just leave that space. So our bubble's starting to rise up. Temperature's decreasing. If temperature's decreasing, which value is changing? The saturation mixing ratio, what's it doing? Yeah, if temperature decreases, the amount of stuff it can hold also decreases. You see, we're going to bounce back to this constantly. You're going to be sick of it by the end of next week. So it's okay, I'm sorry. So saturation mixing ratio decreases. If saturation mixing ratio decreases, what happens to relative humidity? Goes up. So as we take our little bubble here and we make it go up, our temperature's decreasing. We're getting closer and closer to saturation. We're also lowering the temperature of our bubble to its dew point temperature. And then once it hits its dew point temperature, or another way to say it is once relative humidity hits 100%, what happens? We hit saturation and we make a cloud. Now in meteorology, this line right here, this location where we hit saturation has a very special name. It's called the lifting condensation level, or the LCL. The lifting condensation level, the LCL. We have cumulus outside right now. Yeah, so on the break, go outside and take a look at the clouds. Something you notice, have you ever seen cumulus fields before? Just like cumulus clouds. Imagine just like a little tiny puffball cloud, which we've been having like for the past couple weeks, right? What do you notice about their butts? They have really flat butts. They don't work out, they don't do leg day at all, right? So they look like this. In fact, let me change my, I'm sorry to do this. Let me change my graphic just a little bit. Maybe you on yours, you kind of make the bottom, just more flat. So they end up with really, really flat butts. That's because they're forming on this line. This line here is where saturation ended up hitting 100% relative humidity. Cool. Now, as this air parcel was going up, what do you think the lapse rate was? Don't write it down yet, though. Yeah, as it was going up, remember the lapse rate, the change in temperature with change in height? What's the number that we assume that we were using? What would you use on a cross country?
2 degrees.
2 degrees Celsius per 1,000 feet, right? We were talking about it as, do I still have it up there? Oh, I don't have the other one up there. 6.5 degrees Celsius per 1 kilometer is another way for us to say it. That's the average tropospheric lapse rate. We can actually break that up into two different sections now. The first one is going to be from here to here. This is going to be the dry adiabatic lapse rate, or the Dowler. The dry adiabatic lapse rate. Stick with me, we're almost at break time. The dry adiabatic lapse rate is actually 9.8 degrees Celsius per kilometer. Or if you work that out, roughly 3 degrees Celsius per 1,000 feet. Now, why do we care? From here, from the surface, up to our lifting condensation level where our cloud formed, is that moist or dry? How do we define it, right? Is it moist in this room, like by a definition? I mean, we can say it's moist, but by definition, it's dry. The reason why we say it's dry is because there's no cloud in this room. There's no liquid water present right here. So between here and here, there was no liquid water, so it's dry. And we use the dry adiabatic lapse rate for temperature change. So actually, when you're doing your cross countries, if you're below cloud level, you should actually be using 3 degrees Celsius per 1,000 feet. But once you go above the saturation level where all the cloud bases are, then you want to use the next one, which is called the moist adiabatic lapse rate. Or the Maller. Oh, sorry. And this value is 5 degrees Celsius per kilometer. Or a little less than 2 degrees Celsius per kilometer, or per 1,000 feet. Why is it different? Why does our rate of change drop so drastically? So here we're cooling really, really quickly, nearly 10 degrees Celsius for every kilometer. Then all of a sudden that halves once we have a cloud that formed. Remember our heat? What happened to heat when I had this? I'm going from a solid to a liquid. Remember, I'm breaking that bond. I'm using heat energy to break that bond. I was consuming heat in that process. So going from a solid to a liquid, or a liquid to a gas, we consume heat in that process. If I'm consuming heat, then our temperature rate will increase. It'll be something like this, right? But something happened here causing that to change. We went from dry air to moist air, because now we have a cloud that occurred. So remember the reverse of that. If we go from gas, let's see, if we go from gas to liquid or liquid to solid, we're actually increasing the bonds, so we're actually releasing heat in that process. So evaporation right here, because we made our cloud, actually, let me do a little, I don't know if this really graphically makes sense, but we just released heat into the environment. So we're no longer cooling at such a fast rate. We've halved our cooling rate. Does that make sense to everybody? Cool. Any questions on this part? Isn't this cool? When you're on your break, take a look outside. Look at those clouds. This whole process occurred, like little bubbles of air on the ground rose up and made this tiny little puffball with a flat butt. Right? This process is occurring right outside. Now the last thing here for this little block. Why does temperature decrease in our atmosphere? Is the big question. Why in the troposphere does our temperature decrease as we go up? Remember our pressure? It was that kind of relationship, right? It was exponential. As we go up, pressure is decreasing. As we're going up in altitude, our pressure's decreasing. The amount of stuff in the atmosphere, the amount of molecules like oxygen, nitrogen, argon, all that stuff is going down. We have this little equation. Anyone remember that one? You definitely covered it in high school. You probably forced it out of your mind. Anyone know what it's called? Bonus points. Nobody? It's usually like 50-50 if someone remembers it. It's called the ideal gas law. You might remember it from chemistry or integrated physics and chemistry from high school. What's P? Pressure. What's V? Oh, good guess. Volume. Volume. What about N? More bonus points. Number density. Again, bonus points. You wouldn't. What about R? What is it? Oh, good guess. Good guess. Not correct though, but good guess. It's called our gas constant. No, bonus points for that one. And T. Easy. Temperature, right? So pressure, volume, number density, gas constant, and temperature. Now what we can do with this is if we make some assumptions. We're going to assume that we're keeping our volume constant. We're not changing the shape. We're keeping it constant. Number density, we're not adding or removing number of molecules. And then our gas constant is a constant, so we don't have to worry about it. So what we're left with, and we do a tilde here because we're not saying it's equal to, because we're assuming some of these things were held constant. We're assuming that pressure is directly related to temperature. If we increase pressure, we expect, holding everything else constant, for temperature to increase. How many of y'all have ever, actually let's do the reverse. Let's say we're decreasing pressure. So we're decreasing pressure, what do we expect temperature to do? Decrease. How many of y'all have used like a Febreze can or like an aerosol can for spraying stuff, right? You're in college, your parents are coming over, you haven't cleaned the place in months, right? So you grab one of the aerosol cans and you're just like spraying it everywhere. You're going through every single room, you're using the whole dang can right before they get there, right? What's that can doing? It's the temperature of the can doing to your hand. It's getting really, really cold, right? You're decreasing the pressure of the can, which is causing temperature to, in tandem, go down. And the reverse here is true too. If your bicycle tire's flat and you pull out your bicycle pump and you pump it all the way up, right? And you feel the bicycle tire afterwards, or you do it with your car tire, you'll note that the temperature of the tire has actually gone up since you started pumping it. Usually you probably won't notice because you're probably hot and it's 90 degrees outside and humidity is really high and you're pissed off that your tire is broken. You're like, everything's hot, so you're just pissed off. So you probably don't notice it. So in our atmosphere, as we go up, our pressure is decreasing. So what's temperature do? Goes. So the first little piece of this puzzle here is pressure decreases. Temperature decreases, saturation mixing ratio decreases, relativity increases, and then eventually we hit temperature is equivalent to dew point temperature, or relativity hits 100%. Either way, two ways to look at the same thing, and then we get a cloud to form. Any questions on cloud formation? Great. Let's take a break until just like 2 minutes after the 10.
Saturation mean rain?
That's a really good question. So if we look outside and we see all the clouds outside right now, are they raining? No. So there's your answer. The actual precipitation processes we're not going to cover because it'd take like an hour and I just don't think there's like a whole lot of value to it. But there's lots of processes out there, mainly two, that say if you have a cloud, why does one start precipitating and another one doesn't? So there's some other processes involved with it. So just because you have a cloud doesn't mean you have precipitation.
Okay, which makes sense.
Yeah.
And And then this dew point, is that the same thing as saturation?
Kind of. Remember,
The higher the dew point, the higher the saturation?
yeah, so if our temperature outside is 25, so if our temperature outside, we'll just say do some different numbers. Our temperature outside is 30 degrees Celsius, right? And our dew point temperature is 20 degrees Celsius. We need to lower our temperature to this number in order to hit saturation. So temperature, lowering it so that these two are equal, is the same thing as saying relative humidity hits 100%. It's just two ways to say the same thing, that we, at this point, hit saturation.
Okay.
Any questions on that?
I mean, so the higher the dew point, the higher the chance you're going to get more rain.
The higher chance you're going to get a cloud to form.
Okay. And then the
Right.
lower it is going to be clear sky.
Yeah, so let's make an assumption here. Let's say that this ended up only being about 3 kilometers high. So as we're decreasing in temperature as we're going up, this space here was 3 kilometers. So 3 kilometers actually works out to be how many temperatures or how many degrees do we decrease? But in 3 kilometers? Roughly 30. So between here and here, we actually decreased by 30 degrees Celsius, and we hit our dew point right here, right? But let's say our dew point temperature was actually much lower. Let's say it was just a drier environment. In order for us to, maybe 30 degrees was not enough. Maybe it was so dry that we ended up having to go all the way up here. So we had to decrease by 50 degrees Celsius in order to hit our dew point. So that would be the way to look at it.
So dew point is just an idea of where the clouds are going to form.
Kind of. You can use dew point temperature and temperature to get an idea of where your cloud bases are, because you can assume that we're going to be decreasing at this rate, or 2 degrees. Actually, it's like 3 degrees Celsius per 1,000 feet. So if you know that the dew point at the surface here is, let's just say let's say the temperature is equivalent here at the surface to 30 degrees Celsius, and the dew point temperature is 25 degrees Celsius, right here at the surface, and we know that we're going to be decreasing at a rate of, this works out roughly to be 3 degrees Celsius per 1,000 feet. So if we go up 1,000 feet, what's our new temperature?
1,000 feet?
Yeah, we went up 1,000 feet.
Would it be 33 degrees Celsius?
Other way.
Oh,
Remember, we're decreasing because we're going up in the atmosphere.
so it'd be like 20.
So here it was 30, so here would be 27 degrees Celsius. Have we hit saturation yet? No, we're close though. Only 2 more degrees, and we're going to hit our dew point temperature. So this was 1,000 feet, and we go up again, and this is 2,000 feet. But this is where we would actually, so another 3 degrees Celsius, so this gives us what, 24 degrees? But our dew point temperature here was 25, so we actually hit saturation right about right there.
And that's where you're gonna
So
get
that's where our
space.
cloud base would be,
Okay.
roughly.
What?
Yep. Were we missing somebody, or is that everybody? Can't remember. There's no one sitting there, was it? Okay. There's no one sitting here, I don't think either. Okay, so. Okay. Wait, lost my train of thought. Stability. Let's go back to our trusted temperature versus height graph. What's my dash line? There we go. Look at how much we've learned today. What's this layer? Troposphere. You'll notice that I typically have like a little bump here at the beginning, and that's because the surface, typically the air right above the surface kind of keeps the same characteristics for just a little while, maybe like a couple hundred feet before it starts decreasing. That's because the ground stores a lot of energy into it. So when you go outside right now and you go up like 100 feet, the temperature probably hasn't changed all that different from the ground. It just kind of makes like a little insulating layer. But then we get that, then we start the decrease process with the lapse rate. So let's take a look at something here. Let's say that our air parcel here off the ground, this is the environmental temperature in the background. And let's say that our actual air parcel that we have is the temperature at this height is right here. So our air parcel. Remember, I grabbed this air parcel, I kept its temperature, I kept its dew point temperature, and I moved it. I moved it to like Florida or somewhere else, right? I'm just saying that the air parcel temperature is it lower or higher than the environment? Here's our environment. That's if I went outside and measured it at that point, at this point. Let's just call this like 1,000 feet. I went outside and I measured the environment at this point, and I measured the temperature of my air parcel. Which one's higher? Come on, everybody. Wake up. Right here, I'm at this level. So here's my environmental temperature. And then here's my parcel temperature. Which one's hotter? The environment. My parcel is colder than the environment. So what's it going to want to do? What does cold air do? Oh, other one. You had a 50-50 shot. Good guess. Cold air sinks, right? So cold air sinks, hot air rises. Our parcel here is colder than the environment, so it's going to sink. It's going to go back down, right? Stability, we call this stable. Why is my mind breaking on how to spell stable? What's that?
You get over.
I know. It's ever since the pandemic, my brain has never recovered from having COVID twice. Yeah? Yeah, stable environment. Right? I'm 38, I'm getting up there. So we're a stable environment. Does that make sense? Anything we do, the air parcel is just colder than the environment, so it's not going to want to keep rising, right? It's just going to sink. Now, what if our air parcel was actually over here? Y'all can draw like a new little subsection of your graph. I'm going to try and keep the same one just for conserving space. Let's say our air parcel somehow is warmer than the environment. What's it going to do now? It's going to rise. What do we call that? Unstable. Cool, right? Does that kind of make sense? The whole point for us to get out there and make clouds is we need to get the little bubble of air to rise. That's what meteorology is really all about. And I'll show you an equation later called the quasi-geostrophic omega equation. Really fancy name. Really just to kind of make you all be like, oh, meteorology is really cool and complicated and all that. But the whole point of the equation is to solve for upward movement, because that's what we care about. When we have a cold front blow through, that makes things rise. When we have a low pressure system roll through, that makes things rise. If we push air up against a mountain, what does that do? Makes it rise, right? Meteorology is trying to solve that question all the time. Are we going to get air that rises? If we get air that rises, we'll form clouds, which will trigger precipitation processes, hopefully, and create rain, create storms, all that kind of stuff. So that's what we're really trying to solve. So if we have a stable environment, we're not getting anything to rise. If we have an unstable environment, things will rise and make clouds and storms and all that extra stuff, right? One other thing kind of comes to mind here, though, and I'll make a new graph here for this. And I'll make a new little line. Same thing, same units, Z, T, all that stuff. What was that? What is it?
Like a zone stability.
Okay, yeah, great, perfect. What do we call this though? It was an inversion layer, right? So we're no longer decreasing with temperature with height, we're increasing in temperature with height. So let's say that our air parcel, temperature at this height, at this particular height here, is our air parcel hotter than the environment or warmer than the environment? It's hotter, so what's it going to want to do? Is it unstable or stable at this point? Unstable. It's unstable, so it's going to rise. What happens when it hits right here, though? It's going to stay there. Why? It's now the same temperature as the environment. In fact, if it goes up any more, it's going to be colder than the environment, so that'll make it sink back down. This is now a cap. So clouds would probably form here. You'd probably have some little clouds that are just chilling out right at that location. It might even be like a really truly stable environment where you just have an overcast layer of the clouds just sitting right there at that spot. Now, if you went above this cap, if you took your plane and you kind of flew up here, it'd be all nice and clear after this point, right? So it's like a little capping inversion, creating a barrier right there for our clouds to form. We can actually call this conditionally unstable, right? If we can get rid of this cap somehow, then we can cause an unstable environment. Let's say it's like an air mass comes in that's cooler or something like that and actually pulls this back a little bit. We can make that parcel all of a sudden want to go all the way up. That kind of makes sense? I don't think we need to spend too much time on stability, but if you kind of get the gist of stable environment versus unstable environment, and conditional unstable environment being like a situation where we have stability, but we can modify it somehow, like a system can come through, which we'll talk about here in just a little bit, to kind of make it an unstable environment. I think you got the gist of it. The other way that it really hits with stability, it kind of helps some students understand it, is for conditional instability especially, let's say you have a marble sitting up here at the very top, right? This would be conditionally unstable because it has the potential to go crazy, right? All we need to do is just kind of push it, give it some modification to a variable, and then all of a sudden it starts rolling down. The opposite here of it, like a marble sitting here in a valley, this is stable, right? If we push this marble up the side here to right here, what's it going to do? Come back down. It doesn't want to do anything. So you kind of get that? It's kind of hard to draw unstable here because that would be like the marble sitting right here. It's just going to keep rolling. It's on the side of the mountain. That would be like an unstable version. But if that helps, then that's good. All right. We got an hour left. We'll cover 2 topics. Triggering mechanisms and wind. Y'all excited? Woo. All right. Triggering mechanisms. Now there's 4 of them, but we're only going to cover 2. And we're going to, with the next 2 topics, the one we do at the end of today with wind, and then the one that we do beginning of next time, we'll actually cover the other 2. So there's 4 here. I'll go ahead and write them out over here. So one is rising thermals. The other one is orographic lift. Rising thermals and orographic lift. The other one that we're going to cover today are low pressure systems. And the one that we'll cover next time at the very beginning are fronts. So those are our 4, but we're only going to cover the first 2 right here, right now. I need this, and I need this. All right, rising thermals. This undoubtedly is why we have clouds outside right now. Each one of those were formed because of this process. So you have the sun that comes out and hits the ground. Like this. Now the ground is made up of a bunch of stuff, right? If we go out in a plane and we look down, we're going to see that there's a lot of nice open grass, beautiful fields. Then we're going to have some roads. We're going to have some tarmacs. We're going to have some, like, this could be a massively urban environment, like just say like New Braunfels or San Marcos or Dallas, something like that. It could be just a parking lot, and then more grass fields and maybe a smaller version of like an urban parking lot or something like that. But the sun hits all of these with its energy, right? It hits all the grass and everything equally. Now, all these materials aren't made equally. The color, especially of those objects, plays a big role in how much heat it can absorb or reflect. So enter the word albedo. And this is a measure of an object's reflectance. So how much it can reflect energy. A higher albedo means it reflects more energy. A lower albedo means, oh, that's what happened. You were sitting right there. Right? You were sitting up here?
No.
Oh, oh, never mind, we're good. Something just felt off. I'm sorry. So a higher albedo means it reflects more energy, and a lower albedo means it absorbs more energy, right? A black body, maybe you remember that from school, black body absorbs everything. That's what a black body is. So albedo, if something's lighter colored, like white or yellow, like a very, very bright color like that, then it reflects more energy than it absorbs. A darker color like blue or black or brown, those colors will absorb more energy than they reflect. So how many of you have a black car? Anybody in here? Oh, you do? I'm sorry. In Texas, such a rough choice, right? So when you get into your car after being in the growth, like after being in here for a while, the temperature, if we went out and measured it inside your car, is going to be actually measurably higher than how many of y'all have a white car? Than this guy's car, right? Probably in the order of like 5, 6, 7 degrees, something like that. It's actually a pretty measurable difference. That's because the sun's hitting your car. The color of your car, because it's darker, is absorbing more of that energy, causing it to be more of an oven than his car with the white. So green is considered to usually be more neutral. It's kind of like right in the middle. So these areas here, the temperature above them, we're not saying it's going to be cold. It's a hot day, it's 90 degrees, it's whatever, right? But we're saying it's going to be relative to everything else, it's going to be cooler than this temperature right here above San Marcos, or like around in the air above San Marcos, because San Marcos is a more urban environment. Everything has a lower albedo. The temperature here is going to be hotter. All it needs to be is a couple degree difference. Just a couple degree difference. Probably ends up being more than that though. Probably ends up being like 5 or 6 degrees. And this process repeats as we kind of go across our countryside. Right? So if this air is cooler and this air is hotter, what does the air above our city do? Or parking lot? Goes up. Trigger mechanism. Look at that. When you see air rising, I want y'all to get excited, right? Because that's why we're here. We're talking about this. Mostly because we're going to do this same rigmarole constantly. So if my air is going upwards, what's happening to its pressure? Decreasing. If pressure's decreasing, what's temperature doing? Come on, everybody. Decreasing. If pressure's decreasing, temperature's doing what? I want to hear from this side. Decreasing, right? If temperature's decreasing, what's happening to saturation mixing ratio? Temperature's decreasing, our saturation mixing ratio is also decreasing. Remember, cold tea, right? We're holding less stuff. If saturation mixing ratio is decreasing, what's relative humidity doing? Increasing. So here, pressure is going down, temperature's going down, saturation mixing ratio is going down, which then causes relative humidity to go upwards, causing our little bubble here to go up and up and up and up. Eventually, relative humidity hits what? Saturation, which we define 2 ways. What's one way?
Lowering the temperature.
What was that?
Lowering the temperature enough.
Yeah. Lowering our temperature to the dew point temperature. So eventually, temperature equals dew point temperature, or what does relative humidity equal? Yep. And what do we form? And then some upper air up here, kind of just pushes it along. And then another bubble rises, makes a cloud, gets pushed along. It's like a factory, right? And if y'all look outside, you'll see that there's just a ton of little cumulus clouds out there, and they're likely all formed by this little factory process. Cool? Cool process? All right, other one, orographic lift. Okay. Orographic lift. What's orography? That's a big fancy word for something. Oop. Terrain. That's all that really means. So, let's pick a location here. How many of y'all been to San Francisco? Or like Western California, right up against the coast? Anybody? A couple of people? Really cool spot, right? we have some water right here, the Pacific Ocean. And then we have some land. And then what's inland from the California coast? Anyone know? Think back to your geography. Yeah, mountains. You got the Sierra Nevadas. So this is the Pacific, United States, West Coast, Sierra Nevadas, and then behind it, what's behind the Sierra Nevadas? Desert, right? Las Vegas, Death Valley, Nevada. That's like this whole area back over here. And we say it's a desert. There's not a whole lot of life out there because they don't get a whole lot of rain, and we're going to figure out why that is. So here we have air, because generally air and storms across the United States move from west to east, right? So air comes across this water here, hits this land, and then it does what? Why doesn't it go down? Can't go into the ground, right? This is an easy question. Can't go in the ground, so then it goes up. Expected gasps, right? Look at that, upward moving air. Don't you get excited about this stuff? Yeah, there you go, thanks. He's playing along, guys, jeez. All right, so if I have air going up, what happens to its pressure? I told you we're gonna do this many times. And then temperature does what? If temperature goes down, what happens to saturation mixing ratio? Yeah. If saturation mixing ratio goes down, what happens to relative humidity? And then we hit one of two things, which are both the same thing. What happens? Yeah, we lower our temperature to our dew point temperature. We hit saturation that way. The other way to say that is we hit 100% relative humidity, right? And then we form a cloud. Now, this usually results in pretty significant rainfall because we're taking all this air, we're pushing it upwards, giving it nowhere else to go. So we really just kind of like wring out all the moisture from these clouds. Now, those of you that have been to the west coast of California or Oregon or Washington, how do you describe the environment? Is it a desert? No, it's really nice, right? It's very lush, very green. They get a significant amount of precipitation in these environments, right? In fact, little caveat here, when you think of Washington, Washington kind of looks like this. It has a peninsula. Here's Seattle. This Washington Peninsula up here, y'all can visualize is what this actually looks like, right? This is called the Olympic Mountains. And air moving against this Olympic Mountains here, it's actually pretty high. They get over 200 inches of rain per year on this peninsula. It's the largest temperate rainforest on Earth. So definitely recommend if you go to Washington, go to the peninsula, especially the west side. Incredible. It's like the Hoge rainforest or something like that. Everything's just mossy and it's amazing. But all along the coast here to the Baja Peninsula, all along this coast here, this environment, actually starting probably like north of LA, this environment here is just very lush and you know, wonderfully green because you're getting all this orographic lift coming up and over the mountains and creating this rain process right here. Now on the other side of it, we know, actually let me do this. How many of you have been to Eastern Washington or Eastern Oregon? Really not a whole lot out there, but you get the Cascades up here. On the other side is just kind of blah land. You've got Arizona, you've got Nevada, like Idaho, stuff like that up here. There's just there's like a large rain shadow, and that's because as we go up and over this mountain, the air keeps going and then falls down the other side. Gasp. Not really though, because we don't have upward moving air. This time we have what? Downward moving air. So as this air is coming down, what's happening to its pressure?
It increases.
What is it?
Increases.
Increases. Temperature does what?
Increases.
If temperature increases, what happens to saturation mixing ratio? Good job. If saturation mixing ratio goes up, that number down here becomes bigger. What happens to our relative humidity? If relative humidity is going down and down and down and down, and temperature is going up and up and up and up, we're going further away from dew point temperature, and we're getting further and further away from 100% relative humidity. So do we get clouds to form? No. That's not to say that we can't, right? Some sort of weather system could come through and actually create some clouds of precipitation, but it's really, really hard for it to do so. Natural process right here is to keep this area rain-free, cloud-free, generally, right? So how would you describe that over here? I mean, we got like Death Valley right here. You got Las Vegas over right here. You got Arizona. I mean, geographically makes sense, right? We've created what's called a rain shadow. And the other word that we use to describe this air that's sinking down, we call this subsidence. Subsidence. Relating this to being a pilot, I actually got the lucky chance to do some mountain flying last summer. Went up to Colorado Springs and did a little mountain flying trip up to Leadville and got my little certificate of landing at the highest airport in North America. Pretty cool stuff, right? But before we went, we did a 3-hour mountain flying ground course talking about how does wind interact around terrain. Because around here, we don't have any super high mountains or anything like that to be able to affect it. But if you're flying along and you're flying in between, say like 2 mountain peaks right here, you're like flying into a valley, this air is, and the air is kind of moving around from this side. I mean, if you're flying right here, there's your wing kind of outstretched, you're gonna have this massive downforce affecting your plane. Whereas if you're up here, you're probably gonna be having this massive lifting force affecting your plane. So, you know, you got to pick and choose which side of the mountain or like the valley that you want to come in. So this has really like understanding the orography and how the wind is affecting you is pretty important. So any questions on this orographic lift? All right. Move on to the last topic of today. Also one of my favorites. And in here, we're going to talk about low and high pressure systems. All right. Wind. Seems simple, right? Air moving from one place to another. That's how we really define wind. I'm going to draw the United States here. Don't make fun of me. All right, that works out. Baja Peninsula. Here's Mexico. We're right here. Gulf of Mexico, Florida, up to the northeast coast, right? So, you've probably seen these before. You've seen maps of them. Let's say we have a low pressure system right here and a low pressure system over here. And then up here we have a high, and then over here we have a high. So these pressure systems, low and high pressure systems, we have weather because of the sun. The sun doesn't heat the surface of the earth equally. And if it doesn't heat the surface of the earth equally, that can actually cause pressure differences. Remember that ideal gas equation that we looked at with P equivalent to T? Well, the reverse is true for that too. If we have temperature differences, we also can create pressure differences on the surface. Add into the fact also that our earth is tilted, which we really didn't talk a whole lot about, but our earth is tilted. And where was I going with that train of thought? Oh, and you have the sun hitting at different latitudes across that tilt. So this combination of effects does create pressure differences, which we interpret here as pressure systems. And they actually have some really cool interactions with each other. So with these, I'm going to draw some lines around them. How many of y'all been hiking before? Looked at like a hiking map, like a contour map, something like that? So I'm going to make this low. Now you can hold off on drawing until I'm all done. Okay, you can draw. You don't have to really get like exactly the amount of lines I did. I just kind of winged it. But this line, this low here has a ton of these lines. This high here has a ton of these lines. And these ones up here don't have a lot. These lines here are isobars. Isobars are lines of equal pressure. Lines of equal pressure. The way we can look at this is that this low pressure system is really strong. This high pressure system here is really high, or like really strong as well. These two guys are a little on the weaker side. Actually, just for complete sake, I'm going to draw that like there. We've got kind of like a ridge. Now, the way to look at this, if you were looking at a contour map, this would be like a very deep valley or like a crater. Think of it like you're sinking down here to the bottom. If I put a marble right here and let it roll, it would roll to the bottom of this big hole. Consequently, from here, we're climbing up and up and up to the top of this mountain peak here. So this is high pressure, low pressure. Right here is kind of like a ridge of higher-ish pressure, with, of course, this one rising up really high over here. And then, of course, we're sinking down to a little bit of a low pressure right here. Does everyone kind of visually see that three-dimensional? Okay. Why do we care about this? Because right now, if we looked up at a weather map, we'd probably see a bunch of highs and lows all across the country doing its thing. In fact, right now, the big takeaway for this week is there's a big heat dome that's building over here in like the eastern US. There's a big, really strong high pressure system over here this week. We're going to learn high pressure systems make really sunny, boring weather. Lows are associated with more fun, severe / rainy weather, right? So they're going to get really hot up here in the Northeast because of that high pressure system. So this is kind of analogous. This actually kind of works out. Now, the other thing we need to talk about here is called the pressure gradient force. Or the PGF. This is a really cool force. It governs a lot of things in life. And it points from high to low. From high pressure to low pressure. That's the direction the force is pointed. All right. Everyone, take a big deep breath. How'd you do that? Have you ever really thought about, like, how did you physically get all that air into your lungs? Pressure gradient force. Let's go through the process. How do you start out? Do an inhale. Physically, what does your body do?
Like opening ear, just letting the air go in?
Yeah. You have a diaphragm down here. You're lowering your diaphragm, allowing your lungs to expand. So if we go back here and we take a look at PV equals nRT, this time we're going to hold all of these guys constant, and we're only going to deal with PV. So I have to move V over here to the other side. So P is inversely related. I should do the squiggly. Pressure is inversely related to volume. So if I increase volume, what happens to pressure? Think about it. It's confidence. Come on. Decreases. Yeah. If volume was up here and I increased volume, pressure would increase, right? But it's inverse here. So if I increase volume, I'm dividing one by a bigger number, so my pressure goes down. So when you go like this, and you lower your diaphragm, allowing your lungs to expand, the volume of your lungs actually goes up. So volume goes up, creating a low pressure here inside of your lungs. Now, which direction does pressure gradient force point? High to low. So you made a low pressure system here inside your lungs. It's higher pressure out here. So pressure gradient force pointed down your throat into your lungs, and the air was forced down into your lungs. That's how you breathed in that air. Now expel it. Y'all didn't do it. That's okay. There's sickness going around. Maybe you don't want to do that. Right? So when you exhale it, you actually pull your diaphragm up. You decrease the volume of your lungs. So you made this number smaller. You increase the pressure inside your lungs. So now you have a high pressure right here, and now it's lower pressure out here. So pressure gradient force pointed outside. That's how you were able to get the air to go out. Now this principle is foundational to so much stuff. Hydraulics is a really, really big one. Just so much stuff. If you're in an airplane up at like 40,000 feet and someone shoots out one of the windows, something like that, do you know what the pressure inside of a commercial airliner is? It's like right around like 750, 800 millibars, something like that. It's typically pressurized to be like right around the air pressure of like Denver, something like that. So you essentially have high pressure inside the cabin, but low pressure outside the cabin. Because you're flying at 40,000 feet, that's like 10 to 12 kilometers up, you're probably at like around 200 millibars. So it's a significant difference in pressure, right? So whenever someone knocks out one of those windows, inside is high pressure, outside is low pressure. So what happens to everybody? They get pushed out of the plane because pressure gradient force goes from high to low. So everyone just gets pushed out of the plane. Hopefully it doesn't happen to you, but just as an example, right? Everyone cool with how pressure gradient force works? So we have these guys sitting all along the surface of the Earth. So if I were to draw some pressure gradient force lines here, this high kind of points over here to this low. This high here points to this low, just as a basic thing. But remember, this is kind of like a mountain peak, right? So actually, it points in all directions that are lower than it, right? If I put a little marble up here at the top of this mountain, it would roll down to any side of our high pressure system. So a high pressure system forces air away from it. Whereas a low pressure system has air moving into it, right? The Earth is all about equilibrium. It wants things to be equal. It's trying to make everything equal all the time. So this process here of taking all this massive amount of extra pressure is trying to transfer it over here to this area of lower pressure. And that's how we get these pressure gradient force lines. So if we're right here, I mean, where is this? This is like, I don't know, Arkansas, something like that, East Texas. Which direction, if we were only looking at this, which direction would the wind be blowing from? From the east, right? In meteorology, we always talk about wind in the direction it's blowing from, not to. That's not to say, so right now we have a south wind outside. That means the wind is blowing from the south to the north. I can say that we have a wind blowing to the north. There's no problem with that. But if I just say south wind, it's understood that I'm talking about from. Is that cool? All right. Great. What about if I was right here? What wind do I have? A north wind. Yeah. Can things affect that? We could have storms blow through. We could have terrain kind of funneling the wind in a certain direction. So this isn't a catch-all of everything. It's not always going to be true, but in general, that's what our pressure gradient force is doing. Now, in which situation, let's say I'm right here. Which direction right here? Which way am I experiencing the wind?
Southeast.
What's from the west?
Yeah, west, usually westerly, I would imagine right here. So I mean, the wind is generally kind of doing maybe like this whole thing, but you generally have more of like a westerly component at this point. Right. Would this wind be very strong? What about right here? Look at how many isobars are between you and between this low and high. 1, 2, 3, 4, 5, 6, 7, 8. The pressure gradient here is really strong. You're going from an area of very low pressure to an area of very high pressure. So the wind here is going to be pretty strong. What about up here? 1, 2, 3. Only 3 isobars. So your pressure gradient, or your change in pressure with the change in distance, change in pressure over change in distance, up here is going to be very low, and right here is going to be very high. And that is correlated here to wind speed. Any questions on this so far? This kind of sets the picture for us to talk about wind. The other little piece to the puzzle that we need is Coriolis force, which we could really get mathematical with, but I'm going to keep it just to a little picture of the Earth. Here's our Earth. Here's our equator. North Pole, South Pole. Coriolis force. We have a Coriolis force because the Earth is rotating. Because the Earth is rotating. So we're going to say that we are Santa Claus, and we're up here at the North Pole. And we have our factory up here at the North Pole, and there's a competing Santa Claus down along the equator. Maybe he's right here in like the Azores or something like that, right off the coast of like Spain. But he's been setting up this workshop to compete with us. And we don't like that, so we're going to bomb it. All right, so we're going to shoot a missile and blow up his factory. If the Earth was not rotating, our missile would do this direct path. But unfortunately, our Earth is rotating, and it's rotating in this direction. So, and you got to follow me on this. I'm going to do it in a different color. Right? So we fire the missile, and this point is going to keep rotating while the missile is in the air. So it hits, and if we pull that back, hold on. I always do this. It is rotating that way, right?
Yep.
Why is my brain having a fog moment right here? You know, we're going to come back to this. All right, I'm going to give us the summary. In the northern hemisphere, we deflect to the right. In the southern hemisphere, we deflect to the left. Right? I'll come back to this graphic next time. Something's up with it. Or my brain right now. All right, so that's the gist of it. If I'm riding a missile on its way to a destination, then I'm going to constantly get deflected to the right of my target, is the gist of it. If I'm in the southern hemisphere, then I'm going to end up getting deflected to the left of my target. All right. Sorry, failed experiment. So what do we do with this? Let's say we have our low pressure system. It looks like this. Kind of rotates around, keeps kind of connecting up here at the top. Remember I said these are isobars. So maybe this isobar right here is 990 millibars. And this line right here is 1,000 millibars. So as we get closer to the center of our low, the pressure is decreasing, right? So what I'm going to do is I'm going to take a little piece of the puzzle. I'm going to blow this section right here up into a bigger diagram. So this line essentially is this, and then this line is right there. So these are the isobars. So this is 990 millibars, 1,000 millibars. All right. Now what's the scale here? Let's say that this is, let's draw a Texas, awful Texas drawing, just like Texas is sitting right over it. So our scale here is like between Austin and like Corpus Christi, something like that. So it's a tiny scale. We're not talking about like a very large scale. All right, I'm going to take a little parcel of air, and I'm going to put it right in the middle, like right around San Antonio. My little parcel of air, actually, let me do it as a square. My little parcel of air here is a square. I don't give it any pushes in any direction, right? And we're looking down at the surface. So like vertically, this like up into the atmosphere is like this. Immediately, what force starts acting on it? We're not really carrying in the vertical, so it's not gravity. Anyone have a guess? We were just talking a lot about it. Not Coriolis, but, well, pressure gradient force, right? So which direction is the pressure gradient force going to point? High, low, high to low, right? So pressure gradient force is going to push this box this way. This is called like a vector diagram, which we're going to be doing here. So if it starts moving this direction, in the northern hemisphere, we said that the Coriolis force actually points to the right of that movement. So we can add two more lines here. We can say that our movement is going to be in the direction of the pressure gradient force. So it's the same line. And the Coriolis force is now going to start acting on it 90 degrees to the right of that motion. CF for Coriolis force. So that's our first diagram. We let this go a little ways away in time. We have our little box. Pressure gradient force is still pointed that way. We haven't changed our isobars. What's our movement direction now, though?
Northeast.
Why? That's correct.
The gradient force and the Coriolis.
Yeah, our movement was going this way. Our pressure gradient force is pointing this way. Our Coriolis force is pointing that way. So when we add these two together, we actually get a northeast movement. Like that. Now which direction is Coriolis force pointing? Still east. Makes a 90-degree angle with the movement vector. So it actually goes like this. Right there. Coriolis force is going to be 90 degrees to the right of movement in the northern hemisphere. Shall we do it one more time? And we're going to say our movement is now to the east. So which direction is our Coriolis force? South. We're almost there. So what happens to the PGF and the Coriolis force now? Yeah, they're equal and opposite. So they cancel themselves out. And now our little parcel of air travels and stays between our isobars as long as they go, unless we're acted on by something else. So what does that mean? Our low up here, I'll redraw it. our little parcel goes that way. Right here, it's still in between the two isobars, so it goes this way. Repeat, repeat, repeat. Oops, sorry. So which way does our low rotate in the northern hemisphere? Counterclockwise. Yep. It rotates counterclockwise. If we did this whole process again for a high, we would see that a high rotates clockwise. We're kind of speeding through this. Typically, you'd cover like this in an hour and a half, so, but.
Why would we repeat the process of like kind of rotating at 90 degrees? I guess that's kind of what this map is.
So why would we what?
Like you kind of repeat the process of, like you said, like 90 degrees and you move it like another 90 degrees.
Like right here?
Right.
I mean, there's like an infinite amount of steps here. This is just kind of gradually what it ends up looking like. And eventually they end up becoming equal and opposite to each other, so they cancel out, and that's where it stops. We have a special word for this. We call this geostrophic wind. It's air that stays between the two isobars because pressure gradient force and Coriolis force have canceled each other out. Pretty cool. Probably lots of questions on this, and you kind of save them for like next time or until the end. But let's do one last little thing here. This works really well if we have a low pressure system or a high pressure system that's elevated, like off the surface of the Earth. But if it's on the surface, which a lot of the low in pressure systems that we care about are, especially if you're going to be flying, we have to add in one more thing to this, and that's friction. We have to add in the effects of terrain and buildings and trees and stuff like that on the wind speed. So I'm going to go ahead and make a new line. We're going to stick with the same little section though. What did we end up with last time? We ended up with pressure gradient force this way, Coriolis force this way, and then our movement like that. That's what we ended up with last time. And even on your previous graph, if you just want to like continue, if you have some more room, you can probably do that. But just note that this is if we have friction involved. Friction, if we're on the surface of the Earth, what does like having a bunch of trees or terrain do to our wind speed? Slows it down. So now we're going to have I use pink. We'll have another vector here going this direction that's called F for friction. So it's going to counter our movement speed and make it smaller. Now, this will in turn, and you can kind of probably write this underneath it, but this will make our movement speed slower. I'm going to really emphasize it. Makes it smaller. The other thing this does, our Coriolis force is dependent on how fast we're going, right? If I have this marker and I toss it to you there in the back, do you have to like jump to your left to catch it or anything like that because of Coriolis force? No. If a sniper is shooting a bullet a mile down, do you think he has to worry about the Coriolis force because the bullet's traveling really, really fast and the distance? Actually, yeah, he does. He does have to account for it. So the faster you're going, the more Coriolis force is. The slower you're going, the less Coriolis force becomes. So if we decrease our movement speed, what do you think happens to Coriolis force? It also decreases. And if Coriolis force decreases, are we still equal and opposite with pressure gradient force? Nope. So what we end up with is a box that looks like this. Where pressure gradient force is more dominant than all the other forces. So what eventually happens to our box? It gets pulled into the lower isobar. So if we blow up our low over here, it eventually spirals into the low. So the low eventually pulls everything in. Does that make sense? Highs do the opposite. Everything spirals away. Now in our last 10 minutes here, why do we care? Why do we care? Let's see, we have a surface of our Earth right here. And we have a low, and we have a high. What did we say happens to the air around a low? Comes into it. Well, yeah, comes into it. And the air around the high spirals away from it. All this air coming into a low has to go somewhere. So where does it go? It goes up. Look at that. What happens to its pressure of our little air parcel? Decreases. Temperature does what? Decreases. Relative humidity ends up doing what? Goes up. Eventually we hit. Maybe create rain, maybe not, right? The air hits this boundary up here at the top called the tropopause, right? Spreads out. Air around a high sinks. We had a special word for that, started with an S. Do you remember what that was called? Subsidence. And then up here, air converges and then travels downward to replace it. So here we have upward moving air. Here we have downward moving air. We associate clear, beautiful weather with high pressure systems. And we associate severe weather, cloudy, rainy stuff with lows. And this is exactly why that is. Any questions?
I can't remember if I'm just imagining this, but is it true that when you feel like the pressure, like the air pressure is high and it's like super thick, it's actually lower? Or is that?
When you feel it's really high,
Right.
it's actually lower. Maybe what you're kind of getting on is like older people with joints and stuff like that, with like joint problems. They'll usually complain about, oh, my joints are hurting, we're about to have some severe weather or storms or something like that. That's because around the joint, you have a certain amount of pressure that you're used to keeping it together. But if you start lowering that pressure, it causes the joint to hurt. So that's kind of like an old, I don't want to say it's an old wives' tale because there's actually some rooted in truth with that. But you don't have as much pressure, so the joint just starts hurting. Is that kind of like what you're looking at?
I think so.
Yeah. Yeah, any other questions? All right, that covers wind. So next time we cover fronts. Yeah, next time's a lot of more PowerPoint stuff, which I think is really, really, really cool. We're going to be covering fronts, valley, ocean breezes, air masses, thunderstorms, radar, supercells, some other cool stuff. So I've got a lot of visual stuff, like different kinds of clouds, like what you would see if you were flying, and showing like the dangers of certain clouds. So it's really, really cool. And yeah, I'm going to figure out what I was doing wrong on the Coriolis image, so we'll cover that on the beginning of next class too. So any questions? Good. All right. Y'all have a good one.